Hey guys, my name is Muthu Sheriff Kaja. My team members' names are Kavya Rukula and Mohan Goda, and we're excited to present our project on speech emotion recognition using deep learning. And here we're aiming to understand human emotions from speech using artificial intelligence. So motion recognition plays a vital role in virtual assistants, AI chatbots, healthcare applications, and human-computer interactions. So, and existing approaches mostly rely on manually designed rules, which don't really scale well with real-world variations in speech. So using deep learning, we can train neural networks to recognize emotional cues more efficiently, and that can make interaction with AI a lot more intuitive and responsive. So for this project, we used a Raptors dataset, which contains speech recordings labeled with 8 distinct emotions. To make the data more suitable for deep learning, we transformed raw audio into mel spectrograms, and that's a visual representation that captures time frequency patterns aligned with human hearing. This pre-processed step allows our CNN plus BILSTM models to effectively learn both spatial features using CNN and temporal context using BILSTM. That enables accurate classification of emotional states from speech. So before training, we undertook a detailed exploratory analysis of our speech corpus, examining emotional label distribution alongside clip metadata to understand the dataset's composition. We discovered the neutral and happy samples vastly outnumber the categories like calm. So generating STFT spectrograms revealed clear emotion-specific frequency patterns like anger, sharp, high frequency spikes. To ensure our model didn't overlook these less frequent emotions, we incorporated inverse frequency class weights into our categorical cross entropy loss, and that promoted balanced learning across all classes. In our model, CNN layers process the MEL spectrograms, extracting localized frequency patterns. And initially, a convolutional 1D layer with 64 filters helps recognize short-term features, followed by patch normalization with ReLU activation for stable training. Max pooling reduces redundancy before the convolutional layer, so with 32 filters refines extraction. And then the extracted features are then fed into bidirectional LSTM layers, where two stacked LSTM layers process the sequential nature of speech, ensuring the model understands the both past and future dependencies. Finally, the dropout 30% prevents overfitting. Batch normalization stabilizes activization, and the final linear layer outputs 8 emotional categories using softmax activation. And then to train our model, we began with the Raptors data speech dataset and converted each clip into Rebel spectrograms to capture its time. And then we split the data into training and validation, feeding it through the network in batches. To make sure the rare emotion weren't overlooked, we used a weighted cost entropy loss that gave us underrepresented classes extra influence during learning, sorry. We optimized learning rate and ran the model for 50 epochs and applied 30% dropout to guard against the overfitting. Finally, by leveraging a GPU on Google Colab, we dramatically shortened our training time and were able to iterate more rapidly. So finally, the final trained model achieved a 92.27 accuracy, confirming high performance motion recognition from speech spectrograms. And the key metrics such as precision, recall, and F1 score demonstrate consistent classification across all 8 emotions. And the analysis of the confusion metrics shows the minimal misclassification, primarily between emotions with similar speech patterns like neutral versus calm, and high recall values indicated reliable classification accuracy. And comparing it against the traditional SVM on MFCC features, our deep learning approach outperformed SVM-based classification by over 15% and demonstrating the advantages of using a CNN plus BiLSTM models for speech emotion recognition instead. The deep learning model significantly outperformed the traditional methods such as SVM using MFCC features, which struggled to capture complex emotion variations. So moving forward, our enhancements like adversarial training for robustness, draw data augmentation for diversity, and transfer learning to utilize pre-training models can further enhance accuracy and adaptability. So by detecting subtle emotional cues in speech, this technology opens doors in several key areas. In mental health care, it can flag signs of distress during conversations, enabling clinicians to offer timely support. AI virtual assistants could also adapt their tone and responsive based on your mood, creating more natural, personalized interactions. And in customer service, it can also recognize a caller's emotional state, which can allow systems to respond with a genuine empathy that can improve both satisfaction and outcomes. And in conclusion, deep learning provides an effective and scalable approach for speech emotion recognition. This can greatly improve accuracy compared to manual featured based methods. This model has practical application and can be improved further by real-time deployment, adversarial training, and data set expansion. Thank you very much.